Thank you, Paolo, for this nice introduction. I still remember your boomerang experiment when it came out. It really was, I mean, it was very inspiring, because it actually started the precision cosmology and showed how we, the fabric of space-time was expanding and how we could measure it in great detail. So I thought at the time, I'd hope I would, ever find something as fundamental as that. So it's nice to meet you here in this setting. It used to work. Of course, now it doesn't. It's not. No, let's try again. So this is the danger, right? You test everything, and then you go to the telescope. You think everything works, and then it doesn't work. That's and then you see a dark hole in the in this. And I had a movie which actually didn't show on the. Right. Now this is about images. So I had actually lots of images with me to show. Oh, there it is. Okay, that's better. Wonderful. Now there's a thing to click, I think. Yes, okay. Wonderful. Okay, so now this is, and of course, this is me talking about space and time, and it's quite fitting to talk about this here in Bern, because this is exactly the place where the absoluteness and the immutability of space and time was broken by Albert Einstein in this little apartment of his, which is in the Einstein house here in Bern. That's where special relativity was thought about and a few other fundamental papers. And that later led to the theory of general relativity, which then included, of course, black holes as one of the mathematical possibilities. And of course, that was at the time pure speculation. And Albert Einstein himself actually didn't believe in those. He believed the theory, but he didn't believe black holes could exist. He even wrote papers to show that they couldn't form. And he was proven wrong by Oppenheimer, who sort of now became a famous Hollywood star recently. And the way we know black holes form is because we understood the universe better in the last decades. And so if you look up in the universe, we're not only just seeing stars, which look the same every time, we actually see a changing universe. And we see, not just stars, we see dust, we see gas, we see a very dynamic universe. So what you see here is a dust cloud, which is about 100 light years across. That dust actually is, we've been talking about how humans, evolved and so forth. If we want to go back even further, that's where humans came from this kind of dust clouds that we are all made of, because literally we are stardust. And the force that actually drives evolution in the universe, you may think is Darwinian evolution, it's actually gravity. Gravity is actually the creative force in the universe. And you see this in simulation. This year is a simulation of that very cloud over 15 million years, and you see how gravity actually pulls the gas together, and where there is more gas, there will be a more concentration, more gravity, and the gas forms actually stars and protoplanetary disks, and nuclear fusion starts, and suddenly the dust clouds light up, and new stars are formed and planets are formed. And that's happening in a very short time scale. We heard about 2 generations of people, taking over Denmark. Here is 15 million years, but that's short on astronomical time scales where, entire star systems and planets are being formed. And in fact, we are building a radio telescope using the same technology that you mentioned to actually look into these dust clouds. One of them here is shown, the ALMA telescope. And in fact, if you look into some of these areas where new stars are being formed, then we can see these, protoplanetary disks that have been formed. And if you really look at them, this is the size of our solar system, the area of the orbit of Neptune, and we can see how rings are forming around new stars, and each of these rings actually is where probably new planets are being formed. So that's, we see the birth of stars in the universe. But where there is life, where there's birth, there's also death. That's an integral part of it. And that's what we also see. if you look into the universe, you see these structures. And these are supernova explosions, where, oops, there's something I noticed here. That's a little detail. Where's my glasses? Just a sec, because I actually wanted to, there's a little sound effect here, which I wanted to, have you be part of. Just a second. I have another sound, so it's not just for this one here. Okay, so you have stars which come to the end of their lifetime, where all the energy and fuel is consumed and used up. And then there is gravity still, which is also the destructive force of the universe. It's the energy of nuclear fusion which keeps the star alive, but once that is gone, gravity takes over and you have a giant explosion. Now that was the joke, okay? The star will explode, implode, the central region will be compressed, and you have even more gravity, and then the nucleus of the star begins to collapse and become smaller and smaller and smaller. And if we now look at the Milky Way, now that's a picture of Andromeda, which is 2.5 million light years away, 200 billion stars orbiting around the center in like 200 million years. There, in such a galaxy, you would have hundreds of millions of these little stars. But if you go to the very center, you have a very dense concentration of thousands, millions of stars, where here is just one. And so, these stars and these black holes will actually start to merge to the center and start to collapse. And so, if there's one little black hole, it will grow to a bigger black hole, and the black hole become bigger and bigger. And one thing that makes a black hole special, everything that goes in stays in a black hole. And there's an infinite amount of time in a black hole, space, because you can always put more in it. The black hole just becomes bigger and larger. So that's why we think we have in the centers of these galaxies supermassive black holes, which are just the giants among those black holes. And there's good evidence for this. And the evidence comes from near-infrared images of the center of our Milky Way, and this is a famous work that's done by Reinhard Genzel and Andrea Ghez and their groups, respectively. We zoom here into the heart of our Milky Way, and what we see there are a bunch of stars, and we see how they behave over the time scale of about 16 years. And you see that they're actually moving. They're moving, in fact, with 8,000 kilometers per second. They're going around with 8,000 kilometers per second. So if you do this, you need an enormous amount of force to keep them on their orbit. And that force is, again, gravity. Gravity by something that is very, very heavy. A supermassive black hole. And then you see them actually on these nice orbits, which are almost perfectly Keplerian. In fact, they're Einsteinian, but to first order, they're elliptical, like the planets go around the sun. And we can very precisely measure what the mass is. And we know the mass of this dark object to better than a fraction of a percent. It's 4 million times the mass of the sun. When I started actually with my PhD thesis, the very first rough images, were made, and we didn't have any of the orbits, but it showed there's something interesting might be happening there. And then there's this other wavelength that we use, not just optical or near-infrared, we're looking into radio. And that's what we see in the center of our Milky Way, a spiral of gas, and in the very center, a little point of radio. And all the stars orbiting around that point, and all the matter is concentrated in this one point. And around in the early 90s, I was just trying to understand that radio emission, and trying to make a model and explaining this, black holes in general. And one thing that I realized was that the radio emission, if that's a black hole indeed, and masses were uncertain at the time, but then the radio emission at a characteristic frequency would come from directly near the event horizon. So if there's a black hole, it would be illuminated from all sides. And that is very helpful if you have that situation. Because, how does a black hole look like? Well, you've seen that before, and now again, this is how a black hole looks like if you are on a dark background. Then there is nothing to be seen. You need light to actually see the darkness. And that's what you can do if you, have a black hole. And here, these are trajectories of light rays, theoretical ones, how light would behave near a black hole. And because black holes actually curve space and time, light will actually go on curves as well. Like planets, light can actually go around a black hole and actually go on an orbit. So a light that comes on exactly at this distance will actually go on a perfectly circular orbit around the black hole. Which means that all light that comes a little bit closer will actually go around, it will end up in the black hole. So if you're looking sort of slightly next to a black hole, it actually your light ray or your vision ray, so to speak, will go around and you'll end up in the event horizon. You'll be looking into the event horizon sometimes by just looking around the black hole and then into this darkness. Now, if you then surround this black hole with radio emission at this characteristic frequency, and you understand that the emission is optically thin, so it's like a glowing nebula in which you place a black hole, then that's exactly what you predict. You predict a ring of light with a dark region, which we call the shadow of a black hole. And that shadow of a black hole had a very characteristic size, which was directly linked to the black hole mass. And so that was a very clear prediction of what we should be seeing, and we predicted in this paper in 2000 that we should be able to use a VLBI array at these frequencies in sub-millimeter waves to actually see the shadow of a black hole and actually see the characteristic feature of a black hole, which is its darkness. Now, of course, we're doing better simulations these days. We are calculating in big supercomputers how matter and gas, magnetized gas rotates around black holes, how light is actually created, how light is bent. These are very detailed supercomputer simulations that are mastered by a few groups around the world. And this shows here one of these weather simulations around a black hole at all frequencies. But if you then zoom in onto the right frequency, like you would tune in the old days your radio to the right frequency, you would listen to the right radio station, you would actually zooming into the central region, and you should be able to see that ring and that darkness. And that was sort of one of the last predictions that we made before the experiment started. And then in 2017, you referred to this, we did this experiment because in radio astronomy we know how to build world-sized telescopes. You just have to go to the extremes, in this case to the highest frequencies ever done, which hadn't been done before. And this was supported by the European Research Council, but also by NSF. And it was a global collaboration in the end. And we put together 8 telescopes around the world at 6 different mountains. To do this experiment, and this was a nice international team, and there are people actually from our group, all these telescopes, and also from other groups. And then you bring this the data together, you let the Earth rotate, and every telescope adds a certain perspective, and the combination of all these perspectives actually allows you to make an image. One important thing is you need to synchronize the clocks, the telescopes very precisely. That's why you need precise clocks. And you can, predict it. They're actually Swiss atomic clocks that we used. And so there's, again, another nice link to where we are here today. That's a fundamental aspect of the entire experiment. Now, and then you have to analyze the data, and this was done in a collaboration. And this was from our defining collaboration meeting in Nijmegen in 2018, where we got together and discussed the different analysis methods. What we did is we analyzed the data in different teams. Sometimes they were not allowed to talk to each other, get a result like an image independently, and then we would compare afterwards. Did we find the same thing? Then we would start all over again, did a computer supervised analysis method and so forth, because we knew this was the first time we would image a black hole. We only have one experiment, one Earth, so we have to check ourselves and be very critical of all what we do. And so that has become a sign, a characteristic feature of our collaboration, that we really do everything multiple times, multiple methods, multiple groups to check ourselves. And then there was this big moment in 2019 where I had the pleasure to actually present this in the press conference in Brussels, this very first image that we see here in this zoom, where we start in Chile, in the Atacama Desert, but we could have started at any other place in the world, at any other telescope. We zoom into the constellation of Virgo, and this is a zoom of a factor of 1 billion. Different images put together, but that's what astronomy gives you, the large view of the entire universe and the very specific view in one location. And then you see the galaxy M87 in 55 million light years, and you see a plasma jet shooting out, and you zoom further and further into it, and you don't know where it's coming from until you see the heart of it. And then that's what we found, the first picture of a black hole, a bright ring of light and the dark shadow in the very center, and was exactly as large as predicted. And well, you know, some people call it a fuzzy donut, but to us it meant the world, because this is really at the edge of what you can literally do. It's the highest resolution, and you just barely are able to resolve it. But it shows all the characteristic features that you would like to see. And it was a big splash. It was actually in all the newspapers in the world. Internet was going crazy with it. There were 4.5 billion people actually saw that image. And it became sort of an iconic picture of what I'm particularly proud of, actually. It's part now of the photo collection of the MoMA in New York and of the Rijksmuseum in Amsterdam. So it's also has sort of a cultural impact as well. Apart from this, we also pioneered something in that we use these simulations to almost industrial level. So we are simulating this and simulating how a black hole looks like, and that's, if you had perfect resolution, that's how it would look like. Of course, we'd like to see this, but then we'd have to make the world a factor 10 bigger, which we've applied for funding, but we didn't quite get that yet. But then you only not simulate one black hole, but you simulate many. And from this, you can look which one fits the data best and learn something about, how the astrophysics around black holes works. And that is, has been very, very fruitful in the last couple of years. And then, this was just one image. We actually presented finally the second image looking into the center of our own Milky Way, the one where we actually really wanted to start with, the one where actually the mass is much better determined, where we know within a few percent, actually, it's better than a percent, how big that ring should be. And we took the data at the same time, but it took a little longer to reduce because the source is flickering and so forth. And now we're, looking towards the galactic center, and again, we saw the same basic structure, a ring, and the shadow, and again there was no fitting, right? So we couldn't fiddle with neither the data nor with the prediction. It was just smack on in terms of the size of what we're expecting. So that was the prediction. This was one galaxy, and this is the Milky Way. But note, in real life, the one in the middle is, much larger than our entire solar system, and the other one is actually fitting inside the orbit of Mercury. So they are vastly different, factor 1,500 in scale, but they look exactly the same. And that's another prediction of black holes. And you see this here in this graph, which shows sort of the mass of a black hole, and then the shadow size that you would predict. And then you see the size of M87. And then you can, and sort of, the red line is what actually GR predicts. Yeah, so it was within 20% or so was this on this line. Then there were gravitational waves, which you briefly mentioned, which you can also use to infer an indirect shadow size, and that is 8 orders of magnitude, factor 100 million smaller black holes, and you could derive this in hindsight, and that also fits. And then you have 2 points always fit a line. You add M80 Sagittarius A star, which came later and was smack on. So this is theory over a factor 100 million in size, within 10% predicts exactly how big that ring is, and you find that ring. And that's just an amazing triumph of general relativity, which really leaves very little room at this point for alternatives. Of course, we test them, and that's what we can do now. We can test alternatives. Now, what we do in the future, I'm personally involved in trying to expand the array further. We're trying to build a telescope in Africa, because I said we're using different perspectives, but we miss a perspective of an entire continent now. And one of the next things we want to do is we want to make real movies of black holes, not just a still photo. We want to make a movie of it. And that'd be exciting and give us even more astrophysics to see. And we actually couple this to an outreach program, because we are in the country, we want to do this together with the university locally. And you need trained, in the end, people who are excited about science. And you want people who are, students and people are interested in physics and natural science, and so we have this mobile planetarium program that goes to schools and tries to inspire kids, and that's just a very rewarding exercise. And it's done by local students, astronomy students in Namibia now. But just listen to them, just one of these shows.
Yes, like in the lake.
Okay, so you can use...
It's always this, that's sort of...
You guys know what constellation?
Yeah, we get a shooting... yeah, it's...
Yes.
Yeah.
And that's what we call shooting.
Okay, well, you learn about the dangers of space as well.
Yes.
And yeah, that's a very nice program. And in fact, we're going to use some of the Balzan Foundation money to actually give fellowships to students and students in fundamental science. So let me conclude. I think we've seen the shadow of a black hole. And as you said, yeah, no, I think supermassive black holes are real. I mean, they're not just dark, compact objects. These are black holes. We're looking into the event horizon. And relativity, in its most extreme limit, near black holes, extends over 8 orders of magnitude. That's just amazing. We learn a whole deal about astrophysics, how plasma moves around a black hole, how plasma jets are accelerated. We'll actually get much sharper images in the future. First from the ground, try to make movies, and we could go to space. We can make the Earth bigger. The Earth is not enough. Then we can actually get razor-sharp images of black holes. And sub-percent tests of general relativity and so forth. So it's not just science fiction, it's really hardcore experimental tests of relativity. So I think we're really moving into an age of experimental space-time physics here, which is a completely new era in physics. Thank you.